Good afternoon, everyone. My name is Paige Donkin, and my research focuses on the impact of model resolution on Southwest Indian Ocean tropical cyclones. Tropical cyclones account for more deaths and economic losses worldwide than any other natural hazard. Those that occur in the Southwest Indian Ocean can have major economic and sanitary impacts as they strike nations that have fragile infrastructures and agriculture-dominated economies. Studies on global tropical cyclone activity have reported a trend towards more frequent and intense events, and this is an especially important point of consideration in the Southwest Indian Ocean given that the affected nations are so vulnerable. Adding to that, despite high levels of activity, the region remains relatively understudied, so on a fundamental level, increasing our understanding of how tropical cyclones are modeled in this region is very important. Now, how does this tie in with resolution? Numerous studies have shown model resolution to be a critical factor in the simulation of tropical cyclones. Increases in computing power over the 21st century have improved the representation of these systems in climate models, and high-resolution, long-period simulations are becoming increasingly possible. However, they do remain extremely economically and computationally expensive, and so most climate runs are still performed at relatively low resolutions. Because of this, a deep understanding of how model resolution influences simulated tropical cyclone characteristics is central to our ability to interpret future projections. The aim of this study is to investigate the impact of model resolution on Southwest Indian Ocean tropical cyclones. And while we do answer all three research questions in our paper, today I'm going to focus largely on any consistent responses that we see to an increase in resolution. Most studies that have investigated the influence of resolution on tropical cyclone simulation have used a single model with multiple resolution runs, and this can make it difficult to gauge if the findings are applicable to different models. The CMIP6 high-res MIP provides the opportunity to study the effects of resolution across multiple models. By providing a common protocol, it allows for the systematic investigation of the impact of resolution by ensuring that effects due to resolution alone are emphasized. Our study makes use of the results of 4 primavera modeling groups, each run at both a standard and enhanced resolution for the period 1980 to 2009. This table outlines the models that we've used in the study. The first column shows the short names of each model used in the analysis, while the longer names that you'll be more familiar with are shown in the second column. The tracking algorithm that was developed for the study uses minimum sea level pressure as the feature tracking variable. It also includes warm core, vorticity, vertical dynamics, and resolution-dependent wind speed thresholds. To minimize any bias that may be introduced by a resolution-dependent wind speed threshold, only systems that have reached at least tropical storm strength have been included. So looking at our results, first we consider the spatial patterns of cyclogenesis locations and tropical cyclone tracks. Observations show that cyclogenesis generally occurs between 5 to 25 degrees south, with a concentration of activity along this eastern boundary and a weaker tongue extending over the Mozambique Channel. It also shows the highest concentration of tracks between about 10 to 30 degrees south and 50 to 90 degrees east, with no activity near the equator. Era 5 captures these spatial patterns well, but it does show a slight southward and westward shift of this concentrated region. A study by Maui from 2018 reported that Era Interim also featured this westward shift, which resulted in an underestimation of activity in the eastern portion of the basin. All of the models were able to produce realistic simulations of these spatial patterns, but as with the reanalysis, most of them show a southward and westward shift of the concentrated region of activity. Observations show that 67% of events over the study period formed in the eastern portion of the basin, and only 13% formed in the Mozambique Channel. All of the models and Era 5 reanalysis underestimate the percentage of events in the eastern portion of the basin and overestimate the percentage of events in the Mozambique Channel. This same 2018 study by Maui noted this occurrence in CAM-ULAG, which is a stretched grid global model. For both cyclogenesis locations and tracks, an increase in resolution increases the spatial correlation with respect to observations in HAD-GEM and MPI, but it actually deteriorates it in CNRM and EC. So this suggests that resolution is not a controlling factor on the spatial distribution of cyclogenesis locations and tropical cyclone tracks. And using the results of a 2020 study by Roberts, we found that this result was robust with 2 trackers. Now looking at frequency, observations show that over the study period, the Southwest Indian Ocean experienced an average of about 9.3 tropical cyclones each year. the exception of HAD-GEM-HR, all of the models and the reanalysis underestimate the tropical cyclone frequency. I think it's worth noting that at the same resolution, the events captured in ECHR only account for 34% of those captured in HAD-GEM-HR. So this highlights that although resolution is important, it's certainly not the only factor that is responsible for modulating the simulated frequency in this region. Model-to-model differences do play a significant role, and they require further investigation in future work. Here we do see a consistent response to an increase in resolution. In all of the models, an increase in resolution increases and improves the simulated frequency. So combining the two previous figures, this shows an example of my diagnostic output for CNRM-HR. The top two panels provide information on cyclogenesis locations. Panel A shows the actual location with the color of the dot corresponding to the maximum lifetime intensity of the cyclone, and the average annual frequency is shown in the bottom of this panel. And then panel B shows the kernel density estimation of these locations, and the spatial correlation with respect to error 5 is shown in the bottom right of this panel. The bottom two panels give the same information, but for tracks rather than genesis locations. And I think this is quite a useful figure, as it doesn't only provide information on spatial patterns, but also on frequency and intensity. Jumping back to our results, this figure shows the normalized probability density function of 10-meter wind speed taken at peak intensity. Considering this observed distribution, the solid black line, we can see that events over this period covered a wide intensity range from tropical storm all the way up to tropical cyclone category 4 strength. Error 5 is unable to capture this distribution and shows a peak at around 26 meters per second. So this indicates that the majority of systems in the reanalysis dataset were of tropical storm strength. CNRM-HR, the solid yellow line, is the only model that was able to capture the increased frequencies in these higher wind speed tails, and subsequently the only model to capture the full range of intensities that we see in observations. This is unexpected because CNRM-HR actually has the lowest resolution of all of the high-res models in this analysis, but research suggests that a new turbulence scheme used in this model may be responsible for increasing tropical cyclone strength via convection. All of the low-res models, as well as MPI-HR, show a peak at around 18 meters per second, and they're unable to capture the increased frequencies in these higher wind speed tails, so it results in more symmetrical distributions. I do want to note that although MPI, LR, and HR both show a peak at the same wind speed, the high-res run actually has a higher frequency of occurrence in this higher wind speed tail as compared to the low-res run. So as resolution increases, there tends to be a systematic shift of the peak of the intensity distribution towards higher wind speeds, and the relative frequencies in these higher wind speed tails increase. This suggests that an increase in resolution improves the ability of the model to represent the full spectrum of tropical cyclone intensities. This figure shows the velocity potential composite analysis at both upper and lower levels, and while we do discuss the implications for each model in our paper, here I just want to focus on CNRM given the increased intensities in this model that we saw in the previous slide. So both the low resolution and high resolution runs from this model show a greater frequency of events at higher wind speeds than any of the other low or high resolution models respectively. CNRM also shows strong upper level divergence or negative velocity potential across the entire Indian Ocean basin, and this is consistent in both the low res and high res runs. Since strong upper level divergence results in deep convection, this composite might explain the increased intensities of simulated storms in CNRM as compared to the other models. So I just think this is a good illustration of the increased convection in this model that I mentioned earlier. Finally, just to shed some light on the interannual variability of tropical cyclone activity, this figure shows yearly anomalies of the accumulated cyclone energy. Now, in terms of the magnitude of the ACE, we would expect, given the relationship between resolution and intensity, that an increase in resolution will lead to a more realistic approximation of ACE, and this is what we find. But this isn't the case when we consider the trend in ACE. So observations show a clear upward trend between 1980 to 2009 with a gradient of about 2.1. None of the models or error 5 are able to capture the strong positive gradient. HAD-GEM-HR performs best and captures a gradient of about 0.6. This might result from the fact that this is the only model which makes use of stochastic physics schemes, and the inclusion of these schemes has been shown to be beneficial in modeling long-term climate. But in all of the other models, an increase in resolution actually appears to be detrimental to the ability of the model to capture the observed upward trend in ACE. Just some main points to take away from my presentation. In all models and reanalysis, we noted a westward shift in tropical cyclone activity towards the Mozambique Channel. And then in terms of the effects of increasing resolution, we found that it improves simulated frequency, intensity, and leads to a more realistic approximation of ACE, but it does not improve simulated spatial patterns or the ability of the model to capture the long-term trends in activity. Thank you for listening and for this opportunity to present my work.